The sum and difference rule. So how do you find the derivative of a bunch of functions when they're added up together? And the nice thing about this rule is it's very simple. It's what you think the derivative will be. So we've learned the power rule already, and we know that the derivative of x squared, you bring the 2 out in front and subtract 1 from the exponent, so that would be 2x. The derivative of 3x would just be 3, and the derivative of minus 7 will be 0. I wouldn't have to write that, but I can just to show that we've thought about it. And all the sum and difference rule says is that you can just do the derivative of each term separately. So it's really nice that way. That's all. And so this is how we would write it out mathematically, that if you have more than one function that you're adding up, then the derivative would just be the derivative of each one separately. So try the first two. So f prime of x, 16x plus 3. How did you do? Good? And then the derivative of the 4 would be 0, so you wouldn't have to do that. The derivative of any constant is always going to be 0. Again, the way that we showed that before is any constant can be an x to the 0. Then if you did the power rule where the 0 came out in front, well, then you would just get 0 times negative 4 is 0, times anything else will be 0. But we wrote that down, or we had it as one of our things from the first class, that the derivative of any constant is 0, and then the rest of these follow the power rule. For the next one, okay, the derivative will equal, the notation here is just a different way of writing function notation. The derivative, you bring the 2/3 out in front. What happens when we multiply 9 by 2/3? We get 6. Subtract 1 will get us negative 1/3. What happens when we multiply 10 by 1/5? We get 2. Subtract 1. You get negative 4/5. Because if you take 1/5 and you subtract 1, remember that we'd have to use a common denominator here. And then you get negative 4/5. So these first two were straightforward ones. The second one a little bit more complicated just because it has the fractions, but not too bad. But now we start to look at some that aren't as straightforward. So far, we have derivative rules that allow us to take the derivative if you have any kind of power. Then you can use the power rule. And we now know that if we add or subtract things, we can do the derivative of each one separately. But this one, right now, the way that it's written, doesn't follow any of those rules, because we've got an x squared minus 4 all squared. So we either have to figure out a way to change this into one of the forms that we can do a shortcut for, or we're going to have to go back to our definition of a derivative. Would you like to try to change this, or would you like to use your definition of the derivative? You don't change it, okay. So if we actually square this, x squared minus 4 all squared means x squared minus 4 times x squared minus 4. And if we multiply that all out, we'll get x to the 4 minus 8x squared plus 16. Can you see that now we've changed this to adding a bunch of powers, and we can do the derivative of each one separate? So the derivative of x to the 4 will be 4x cubed minus 8x squared. The 2 comes out in front. Subtract 1 from the exponent. And the derivative of 16 will be 0. So one of the strategies we use is how can we change something in a form that we can't do a shortcut for the derivative for into a form that we can. And this would be the quickest way to do that. Here we're really going to have to use our exponent rules. First of all, I'm going to change my cube root, to an x to the 1/3. Right now we're multiplying, right? An x to the 1/3 multiplied by the 6x squared plus 3x. So it's not in a form that we can use one of our shortcuts. But if we distribute this x to the 1/3 through, then maybe it will be in something that is the right form. So it goes back to our exponent laws. What happens when I multiply an x to the 1/3 times a 6x squared? What do I get? 6x to the, not 2/3, 7/3. How do we do that? Right, when we multiply, we add the exponents. It's much easier to see when you had nice numbers, like x to the 5 times x to the 4 is x to the 9. When you have fractions, the same rule applies, but now you have to think, well, how do I add 1/3 plus 2? I would need to get a common denominator, and then that would give me x to the 7/3. Same thing when we multiply the x to the 1/3 times 3x. Can you see that you'll get x to the 4/3? Because 1/3 plus 1 is the same as 1/3 plus 3/3. And now we can take find our derivative. What happens when you multiply 6 by 7/3? Subtract 1 from the exponent and you'll get 4/3 left. What happens when you multiply 3 by 4/3? Subtract 1 from the exponent. Okay, so if you see, be creative. How are you going to rearrange this and write this in a different form so that you can use shortcut? Method number 1. What you can do with the 2x squared plus 9 all over 3x is you can break this up into two fractions. It's kind of the opposite of adding fractions. So what I'm going to do is I'm going to have the 2x squared. Oh, got my pen right in there. Sorry. I'm going to have my 2x squared over 3x plus my 9 over 3x. Okay? So let's just look at the first line here. And all I've done is I said, well, here it's one fraction. I could take a step backwards and imagine it two fractions added together. And they'd be both over 3x. Because if I had to add these two fractions together, they'd have a common denominator. I would get 2x squared, 2x to the 7 plus 9 all over 3x. So we're just taking it a step backwards here. But if we do that, in our first fraction, can you see that the x to the 7 divided by the x will simplify to an x to the 6? And our second fraction, did I factor out a 9 somewhere? Okay. Well, here I did 9 divided by 3, and that'll give me 3. And then I moved the x up to the numerator by making x to the minus 1? Yes? I'll come see yours in a second. Now, we've got it in a form that we can do the derivative. The 6 comes out in front. 6 times 2/3 will be 4. Subtract 1 from the exponent, you'll get x to the 5. If the -1 comes out in front, you'll get a -3. Subtract 1 from the exponent, you'll get a -2. A second method to solve this whole thing is you could move that x to the minus 1 up to the top to begin with. Okay? So I have the x in my denominator, and all I did was say, well, that x in the denominator, I can move it up as an x to the minus 1, and then I can distribute that x to the minus 1 to each one. That still gives me my 2x to the 6 and my 9x to the minus 1. Now it's all divided by 3. Having an entire fraction all divided by 3, you can think of that as multiplying by 1/3 out in front of the fraction. And when you distribute that 1/3 through, we get 2/3 x to the 6 plus 3x to the minus 1. The same thing that we got in our first method as well. So it took us a little bit longer to get to that same thing, but in the end, our derivative turns out to be the same. Yes? So here's one to work backwards. If you were given the derivative and it was a 20x cubed plus 5, what do you think the original function would be? That first one is going to have an x to the 4. And if the 4 came in front to make a 20, what number would have had to be in front? A 5. So that's sort of the idea of how I go about figuring these ones out. Then if you just have a 5, originally it would have been a 5x. Of course, here you can insert your favorite number if you want to, right? Or you can say just plus c. You wouldn't have to write anything there, but any constant that's there would still be the right answer. And that's why a question like this says find a function, just one, because there's a lot of them that would work. So you wouldn't need to write that plus c, but if you did, or if you wrote plus 15, or if your favorite number is 37, you can write that in. It makes you very happy. That's great. Okay, we're going to take some time to practice some of these. So take out your textbooks.